Hello, everybody. I am so incredibly sad right now. Essentially, what happened is that Ray and I recorded the entire episode only to realize afterwards that I was using my default MacBook microphone instead of this crispy, amazing sounding microphone. So, oh god, I'm like, this is horrible, but we don't have really a choice. So this is just a little disclaimer. The entire episode, my audio just sounds not great. So I'm sorry, but yeah. I hope you guys enjoy the episode.
It's the language of the universe.
But I don't understand it.
Hello, everybody. Welcome back to another episode of the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray. And we welcome you to episode number 67, where today we're going to be talking about something that everyone knows, something that everyone sees.
Not everybody.
Okay, shit. I'm sorry. But the topic of today's conversation is light. Yeah, sorry. That was kind of like not my intention. That was not my intention whatsoever. It was just a way of kind of hyping up the topic. So today we're going to be talking about light, the electromagnetic carrier, and obviously a little more into the physics of light, a little bit about the spectrum itself, and just diving deep into what surrounds us everywhere.
Wait, one thing that's actually pretty interesting about blind people is that if you think about, like, if you close your eyes, you're like, oh, This is what blind people see, but it's like, hold on 1 second. You see black, right, when you close your eyes, but you're still seeing black. Blind people just don't see at all.
They
right?
still see.
So,
I mean, what do you mean? No, what do you mean? They still
don't
see black.
No,
like they still see
don't
nothing.
See. Ray, they don't see.
It's
That's
not
what
like they
being
don't have
blind
eyes,
is.
man.
Like, okay, I'm not talking about legally blind, because some people can actually see like shapes and shadows.
So you're talking about like completely, totally.
I'm talking
blind.
about like if you like don't have eyes, you don't see.
Obviously, that's different.
Exactly.
If you don't have eyes. I'm not saying if you don't have eyes, bro. I'm saying if you're just blind. Like, some people. Again, I'm not very good with the biology here. I know it's a simple explanation, but I have not made the time to search it up. But I know there is a reason for why people can be totally blind with their whole pupil situation. And I'm pretty sure that they still have the eyes, and I'm quite certain that they just see nothing, which is blackness.
So topic of the week is light, everybody. We're talking about light and photons, and everything related to light. Why? Because light is so mysterious, amazing. It's the gateway to quantum mechanics. It is, a part of special relativity, general relativity. Everything kind of hinges around what we call light. And so, before we actually get into the topic of light, we have our news segment that we run every single week. We are actually now past 10,000 followers on Spotify. Let's go.
That's amazing.
Let's go. I think right now we're at 10,200 and something.
Wait, 200 already? Really?
Yeah.
Hey, that's decent. Yeah. So, thank you too. Yeah. Wow, man, seriously. We've been wanting this for quite some time, eh? The 10K was always a big number in our minds. I mean, who doesn't, right? And we've always been.
I'm waiting for 100.
The 100 is the next obstacle for sure. Well, the 50 is the next one, then 100 for sure. But I think the 10,000 follower mark, especially only on Spotify, our cumulative followers were 10,000 quite a while ago. But this is just our Spotify, because Spotify is like our number one platform by far, like a major lead. So thank you to everyone that continues to listen there. And we always recommend and encourage you, if you want to ever see us, hop on YouTube, give us that quick subscribe, comment for the algorithm, let people know about the Math and Physics podcast.
Yeah, we also passed 150,000 downloads.
Decent.
So that's cool. That's cool, I guess. Thank you to everybody who's been listening. Make sure to follow, subscribe, all that stuff. And make sure to leave a comment under this YouTube video in order to be the comment of the week, who this week goes to Shreya.
Okay.
He says, "Hell yeah, this is exciting," referring to the merch that we announced last week. She said, "My broke ass gotta start saving." Hey. Yes, sir. Hey. Okay, so speaking about merch, by the way, announced last week, what we have just like very simple designs, releasing some t-shirts. We're gonna be posting on Instagram. I'm gonna release like I think like 4 different like images, and then you guys can go and vote on Instagram, and whichever one gets voted the most, we're going to do a giveaway. We're going to do a giveaway of our very first piece of merch. So we're going to do something where you have to share the post. I don't know, do like
we can think about that.
Something like that.
So Shreya, so you don't even need to worry because your broke ass doesn't matter. You don't need this is a giveaway. So I just wanted to point that out.
Okay. Well, yeah. After the giveaway, no, you said that wrong. But anyways,
you know what I meant, though. You know what I meant, because it's the way she said it in the comment.
Yeah.
It just I wanted to replicate that.
For sure. So after the giveaway, I think we're gonna open like on a website. We're gonna open the orders for like 2 weeks, something like that. After the 2-week mark, boom, we're gonna actually make the t-shirts, ship them out, and that'll be our first round of merch. So obviously keep your eyes peeled on Instagram for amazing Math and Physics podcast merch. Anything else, Ray?
I don't think there's any other news. Is there? Where YouTube, we hit I think our 700 subscriber mark, so that was nice. Cool. So we're chilling on YouTube, close to the 1,000 subscribers. So get us there. If you guys, all the listeners out there, always hop on YouTube, search us up, Math and Physics podcast.
So here we go. Jumping into the topic of light.
Light.
Why is light so interesting? Okay, one of the things we talked about this back in episode number 3, constants in nature. The speed of light is a constant. And it doesn't matter at which velocity you're going. It's the same speed in every inertial frame of reference, which is a little bit counterintuitive, but nevertheless, it's true. The speed of light is a constant called c, and it's like 298, 99,000.
Very close to 300. Yeah, exactly.
Yeah, it's very fast. Very. How do you say, unnoticeable. That's why when you turn on the light in your room, you don't actually see, the delay between you turning on the light and the light reaching your eyes, because it's so incredibly fast.
That's also to do with the speed of electrons in the wire. But I get your point.
Yeah. Well, actually, that's not quite true.
No, because electrons, but I know what you mean, because technically electrons are not flowing in the wire because they'll always be present in the wire, so it's like kind of instantaneous. I know what you mean, but what I was trying to say is
the signal moves at the speed of light as well.
Yeah, I was just saying it also depends on that, and then that light emitting. So,
which is still unnoticeable. I think the number, I think the figure is like in 1 second, light can go around the Earth 9 times.
Isn't it 7 times?
7? I thought it was
some
9.
number, big number.
Yeah,
a big
which
number.
is like actually incredible. And then another quick fact, if you didn't know, it's like 8.5 minutes to go from the sun to here, and like 1 second to go to the moon at the speed of light.
Probably really fast. But I know 8.5 minutes for the sun for sure, like 8 minutes 34 seconds, something like that. But I'm not too sure about the moon. But anyways, all of this that we're talking about, interestingly enough, notice how none of it is actually light. It's all to do with the speed of light. You know what I mean? Like everything that we talk about, especially, you know, with relativity, when we're talking about with, special or general relativity, any form of relativity that we talk about photons in, or when we're talking about these, this mysterious force traveling at this, you know, this infinite, almost capped speed of the universe. What's interesting isn't the force, which we will be talking about today, which is exactly the point of this episode. But as we're discussing right now, what's also interesting is the speed, and that's the more interesting thing. The fact that the speed is somehow, or at least to our knowledge so far, the fastest thing anything can possibly attend, or anything can possibly reach to. And everything in the universe is dependent on that speed. Everything. Relativity itself, right, is based, like time, how much it dilates, is based off of your velocity from the speed of light. So it's completely based on the fact that that guy is constant.
Yeah. And one thing that should be emphasized is it's not only like atoms that can't move quicker than the speed of light. It's also down to information itself that can't travel faster than the speed of light. For example, if Ray, you're 1 light year away, and I wanted to I had an idea in my head that I wanted to put in your head. There's no way that idea can get into your head, not by Wi-Fi, Bluetooth, there's no way. There's no way in the universe that the idea in my head can reach your head.
Quantum
in less than a year. That doesn't violate the...
It doesn't. Exactly. No. It doesn't. Yeah. I just wanted to say quantum entanglement because we were talking about the whole information traveling at this cap speed and how it was, you know, literally the biggest, one of the biggest mysteries in physics. Einstein himself, you know, called it spooky action at a distance, the famous phrase, because even he himself did not believe that was such a thing, right? Somehow not information, but just superpositions transferring instantaneously can lead to a decoding of information. So that whole process in physics is so interesting. And yeah, seems to destroy the whole information thing, but doesn't really, because the whole point of this thing is fundamentally why is this photon, or this light that we call it, why does it travel at this fundamental speed? And it's all got to do with, well, what is light? Light is just a combination of electric and magnetic waves. And the particle that we say that carries the force, and we're going to talk about this in a sec, I'm getting ahead of myself, I know, but the particle that we say that carries this electromagnetic force, the photon, is said to be massless. Now, any particle in the universe that is massless will travel at the speed of light. So the speed of light isn't really because of light, it's just the fastest speed possible. It's just that light happens to be massless, fundamentally speaking, so it travels at this fastest speed that we happen to call the speed of light. Even a gluon, for example, I know I'm getting a little aside here, but even a gluon, for example, the strong nuclear force, travels at the speed of light because it's massless. So all massless particles, why? Because what just happened? Sorry, there's a small connection issue. I think we're good. You're muted though. Yeah, so gluons, fundamentally, due to their property of being massless, do not interact with the Higgs field. Quick thing to episode 64 with Dr. Don Lincoln, where we were talking about the Higgs boson and the Higgs field. And particles that don't interact with this field travel at this enormous speed that we happen to call the speed of light, right? And that's basically, you know, the whole light, the whole reason the speed is so cool, you know. And
not only is the speed intriguing, but as I said earlier, photons, for me, I mean, there are other entryways, I guess, to quantum mechanics, but to me, photons are the true gateways to quantum mechanics, in multiple ways as well. The first way is that photons are packets of energy, packets of bite size. I wouldn't say indivisible, because you can have like different energy photons, but
No,
they come in.
It's totally divisible, right? It's HF, right?
Yeah, but I mean, like, one photon itself is its own like singular quantized packet of energy, right? So what does that even mean, right? Because did we ever really define like what a quantized packet of energy
No, I
is?
don't. I mean, I
Yeah.
think we went over it in an episode where we were talking about like quanta and like the whole definition of where quantum came from, maybe.
Oh yeah.
But I don't think we went into it. You can go ahead.
Well, anyways, it basically just means that, if you are emitting a photon, then you, like, let's say you're emitting a photon at frequency, or at wavelength lambda, then what's the equation again? We haven't done this in,
Yeah,
in like a
it's
year.
the summer, guys. It's the summer.
Energy equals
E equals HF is your fundamental
right,
equation.
right. E equals HF. So you divide H by the wavelength, and you get that set amount of energy. So,
or
for example, when
H times velocity over the wavelength, because frequency equals velocity over wavelength.
Yeah. So when you look at the what's it called, the photoelectric effect,
yeah,
boom, that's when you get to see like the particle side / like quantized wave packet side of photons, where you can actually see the effects of like singular photons being absorbed by electrons and all that stuff. But when you start looking at different experiments, different setups, you start talking about waves. And as I just did, which is kind of very counterintuitive, which is, the entire topic of quantum mechanics is counterintuitive. But notice how I was talking about quantized photons that are, particle-like, but I use the word wavelength when describing the energy of this photon. So where does the wave actually come into play, right? Well, this was one of the greatest debates of all time, excluding the Niels versus Einstein debate. And it's what is light? Is light a wave? Is light a particle? When you get into high school physics, they kind of just tell you it's both, and just accept that it's both. And then when you get to university, they say the same thing, because truly we don't know why. We don't know why light has properties of waves and properties of particles, depending on when and where and how you look at them. But it's one of those properties of the universe where maybe eventually we'll have an explanation, and maybe not.
It's just that, but I think there's kind of, I mean, my interpretation of that at least was that light is in fact fundamentally a wave, but like traversing the universe, like it is fundamentally a wave. And wait, how was I trying to think of this? Because it's kind of interesting when you have to describe, because when you say they're packets of this energy, you're kind of describing it in terms, as you said, of particles, right? And when you say, okay, I'm directing it towards, like, for example, if let's say some explosion happened somewhere, and when I'm saying explosion, I'm saying like stellar, astronomical, supernova, or some kind of explosion, the light, the light would totally just reminate outwards in all like circular direction, right? So I was just thinking,
there's more than one.
I guess that's
photon,
not really.
right?
No, not really. I'm trying to think of this as I'm talking about it, so I don't really have my thoughts, truly thought about, because I was thinking about this interesting idea right now. But I don't think, maybe it's not fundamentally a wave. Maybe it's just fundamentally both. Because I know the whole thing of the wave particle duality agreement is that it's mathematically a wave, right? That's the big thing. That mathematically we can represent this and we can see properties of it being a wave. But when we look at it, it behaves like a particle. So,
I mean, not always, right? The double slit experiment. that's us looking at it being a wave, right? Technically, I guess, if you know, technically it's the illusion of it being a wave, but still.
Yeah, it's
because at the end of the day, you know, if you're
definitely interesting, yeah.
If you're what's it called? You're emitting photons at a very slow pace, right? Like one at a time through the double slit. You're going to be seeing just like single photons hit, but the more and more photons you actually send out, the more it starts to give you this superposition. What's it called? What's the word I'm looking for? Constructive interference pattern. Yeah,
interference patterns.
Yeah, interference. Yeah.
Oh wait, that was the end of your point. Sorry. So
yeah.
So the whole interesting thing about this about the idea of photons. Now we've spoken about them, the whole wave particle duality situation, because fundamentally speaking, you can think of these photons that we talk about as these waves, and that's a whole that, you know, opens up a whole new idea or a whole new wave of thinking about light, right? Because initially the double slit experiment was done on light, on photons, and then the idea was then traversed onto electrons as well. And then similar results were seen with electrons, and then saying, okay, electrons are not actually particles either, but even we can represent them as waves, like in the electric field kind of thing. So,
and it turns out everything has a wavelength.
Exactly, right? So the whole wave particle duality thing kind of got people thinking about, well, okay, if it applies to light, why can't it apply to other things? Why can't it apply to all other particles of nature? And interestingly enough, all other particles of nature, these force-carrying particles, have these fundamental wave-like properties. And this wave-particle duality nature gives us a very succinct way to understand it. Now, why, though? Because waves, so when we represent particles, we have a position and we have a momentum. We have those two variables defined. When we have a wave, however, that's not the case. We can have a varying momentum and a varying position. Now, when I say varying, that might make not much sense to you, but a nice way of thinking about it is if you're trying to measure it and it's always moving back and forth between 3 and -3. So it's like moving back and forth between 3 and -3. So it's kind of like, it's an uncertainty of position. So it's kind of varying between different positions. And the same thing is happening with its momentum. And that fundamental property of it being a wave is what allows us to transition into quantum mechanics, right? So moving into quantum mechanics is when we realize these uncertainties and quantize these equations, right? And the whole goal in quantum mechanics is to quantize an equation of motion and to understand, okay, this is happening in the real world. Let's see if it happens in the quantum realm as well. So then they applied it to the quantum realm, understanding light and understanding all of this whole deal. And turns out, again, this whole wave particle duality situation with all these particles fundamentally being waves can directly be applied into quantum mechanics, right? Now we don't want to maybe get too deep into it, but the most important notion of quantum mechanics, a very important notion of quantum mechanics, is the wave function. And as described by its name, it's a wave. It's a function that's an oscillating function. So it's a wave. And making the connection between this wave function, what we've defined, and what we see in the real world, this wave-particle duality, is what allows us to quantize light, right? And make that connection between them.
Wait, in what way does the wave function allow us to quantize light?
No, I'm saying the fact that light has a wave-like property, and obviously we've defined quantum mechanics around these wave-like properties. So we have a thing like the wave function. So I'm saying we can apply the wave-like properties of light into quantum mechanics via things like the wave function is what I'm trying to say. right? Like via using those states, we can apply it in quantum mechanics.
I feel like those are two different things, though. You know, like the wavelength properties of light and like the wave function of an electron. It's not really the same, like, you know, because an electron
I'm just trying
can
to
have
make the relationship in quantum mechanics, because the wave function is fundamentally a quantum notion, right? So I'm trying to make the connection between the wave function in quantum mechanics and the wave-like properties of all these particles. So that's what I'm saying. We can connect it to quantum mechanics via that waveness, is what I'm trying to say.
I guess. But something that's even more incredible, if you can even get more incredible.
Oh my.
Is that, as we talked about, electrons have energy. You know, they have different, like for example, a hydrogen atom, probably my favorite atom of all time, right? 1 proton, 1 electron. There are different energy states depending on the energy level of the electron. And so what does that even mean, right? The electron can absorb and emit photons. And as we talked about, photons come in set amounts of energy. And so one thing that we can talk about a little bit is spectroscopy, right? So when an electron, and also before I start talking about this, maybe for quantum mechanical reasons, there are set energy levels that an electron can occupy in a hydrogen atom. And this has to do with like the orbit cloud and all that stuff. You know, there are some orbits it just can't have, and some orbits that it can have. And depending on the energy that it has and the distance away from the nucleus and all that good stuff. All that to say that there are like definite, like unique, you know, energy states that an electron can hold. And to go from lower states to upper states, it has to absorb a photon, meaning that it absorbs energy, gains energy, moves up to an excited state. And when it comes down from a higher excited state to a lower state, it has to emit a photon. And, okay, this is probably like one of my favorite topics to talk about, because I remember being in class learning about this, and it made so much sense.
Is this electromagnetic theory?
No, this was in first year when we talked about spectroscopy. And so, just for like reference, if you like burn hydrogen or whatever, and you analyze like the spectrum of light that comes off of that flame or whatever, you see like missing lines of different wavelengths. And this was actually like a mystery for a long time. People were like, okay, well, there's missing lines in hydrogen, and then in different elements, there were different locations of lines that were missing. And everyone was just like, okay, you know, whatever, we'll figure it out later. And some people actually made mathematical guesses that lined up pretty well. Essentially, it was like a mathematical sequence where, you know, you plug in like the initial, where the initial line is, like let's say like the lowest wavelength, and then you plug it into the formula, and then it generates the next wavelength, and then the next one, and the next one. And some of these formulas were actually kind of accurate, but not perfectly accurate. Anyways, the explanation is actually tied to quantum mechanics and these energy levels that electrons can occupy in an atom. So, as I said earlier, to move down from an excited state, let's say from the first excited state to the ground state, which is just, you can call it like the energy zero. As we know, energy is relative, right? So if you just define the energy to be zero at the ground state, and then boom, makes your life a tiny, tiny bit easier. So the first excited state, to go from the first to the ground state, you need to emit a photon, which holds the exact amount of energy that you need to be at the first excited state, right? And as we talked about a little bit earlier, the energy is related to the wavelength of a photon. And so as an electron emits a photon that goes, I guess it would make a little bit more sense to talk about absorbing. So let's say an electron absorbs a photon that gives it the exact right energy to go from the ground state to the first excited state. Then, you look at the spectral lines of the hydrogen. That's where the electrons went. Or sorry, that's where the light went, the photons, right? There were missing wavelengths
lack of light.
in the spectrum. And you say, okay, well, why am I not receiving photons of this exact wavelength? It's because the electrons in the hydrogen atom needed this specific amount of energy to go from the ground state to the first excited state. And so those photons were taken up, absorbed by the electrons, and now you can't see that specific wavelength. And the same thing goes with going from the second state to the third state, or so on and so on. And these specific jumps actually have names. One of them is called the Lyman series. One of them is called the Balmer series. I don't remember the other ones off the top of my head.
I remember our quantum mechanics prof putting it in that graph of energy states. I do remember. I think. But there are different names for those jumps, right? Mm-hmm.
Yeah, but to me, this is the most insane discovery ever, right? Because people were studying spectral lines way before quantum mechanics, and they were just like, I have no clue what I'm looking at right now. And then all of a sudden, you have this crazy theory about how angular momentum is quantized in the orbit of the electron around the nucleus, and mathematically you can work it out. You can say, okay, if the electron holds the first excited state amount of energy, it should be here, whatever. If it emits this amount of energy, goes down to the ground state, it should emit a photon that has this much energy and has this wavelength. You look at the spectral lines and it matches it perfectly. You say, oh my God, this is actually for real. Quantum mechanics is not just some weird theory that doesn't work. One of the nicest confirmations. Well, I haven't gotten that far into it, but to me, as an introduction to quantum mechanics, it was a very nice confirmation of this is actually a thing.
Interesting thing about these photons now being emitted from these electron jumps. So contrary to the absorption spectrum that you were talking about, when the electron is absorbing a photon and you see a dark line, you also see an emission spectrum from if let's say you have for example, if you have a telescope in space, for example, and it's not being absorbed by the atmosphere or anything, so there's nothing there, and you are, let's say, observing some hot gas or some kind of light bearing astronomical object, right? And you receive the incoming light. Again, a spectrometer is basically a fancy prism. That splits the light and shows it to you on a spectrum. And that's the nicest way to say it. And when the light receives through that telescope, splits up, you would see, primarily a dark band, contrary to the absorption spectrum, and you'll see just lights, individual bands of light. Now, these individual bands of light is what we call the absorption spectrum, right? The opposite of that emission spectrum. The individual bands of light is what we call the emission spectrum, opposite to the absorption spectrum. Only difference here is this is where the photon was emitted, right? So contrary to when it's being absorbed, it's primarily dark, but in some certain energy levels, the electron is able to go to a lower state and therefore release a photon. Now, here's where cool stuff happens. What if we're not just talking about hydrogen or something releasing, or just a primordial element releasing one of these photons? What if instead we're talking about an atomic nucleus, like a radioactive nucleus, releasing these high energy photons? Now that is familiar to what we call gamma radiation. So gamma radiation, I don't know, I just want to plug gamma radiation because it's really cool. It penetrates through everything. It's the most dangerous form of radiation, and it's basically like a fancy way of saying a radioactive element is emitting a high energy photon. So all of this relationship between light and the electron is seen in gamma radiation, especially, right? So if we have, for example, in atomic bombs, I know this is kind of a pessimistic or like a doomsday example, but in an atomic bomb, the gamma radiation is what first kills you, right? Because that burns straight through tissue and just goes through the body through and through. It requires like half a block of lead to stop it, right? So, and that's all just a photon, right? That's just a high energy photon. That's what's insane about it. This whole insane thing that kills people, it's just it's light. It's just high energy light, right?
Yeah, and one thing about photons is that they don't just come in the form of visible light. Interesting. This is actually a very interesting comment that I heard. And like the reason why human eyes have a specific visual spectrum is because of our sun, right? It's optimal for our survival to have this range in like being able to see these photons. You know, why can't we see infrared? It could have been the case, right? So imagine this. This is actually quite an interesting topic. Imagine if our sun was cooler, it was less hot, and the black body spectrum of our sun was a little bit shifted to the right and peaks a little bit more to the right. And so for us, or let's say for creatures on Earth.
By the way, when you're saying right, you didn't even explain it. When you say right,
right.
Like longer wavelength.
Yeah.
So right, lower energy.
Yeah, longer wavelength, lower energy. That's what happens when your sun is cooler. So imagine our sun is cooler. The black body spectrum peaks at a lower wavelength.
No,
now,
higher
wavelength. Sorry, lower frequency. Sorry. So does this mean? And I'm pretty sure. Like we don't have any confirmation, but I'm pretty sure the answer is yes. Does this mean that people who live on this planet, their eyes would be accustomed to a lower peaking on the wavelength side, right? A lower peaking visual spectrum, which means to us they would have infrared eyes. And to them, we would have like higher energy absorbing eyes, right?
Well, I mean, there are animals on the planet that have like, eyes that can see more than the visible spectrum. It's just that we don't.
But I guess.
So many animals can see ultraviolet.
Yeah.
Is like an obvious example. Infrared, I guess, is the other way, but I'm saying it's a possibility that maybe you are. I mean, I'm like very positive you are correct. It is an evolutionary thing. It most definitely is, right? Like, why else?
Exactly.
It's most definitely an evolutionary thing, but that isn't to say that eyes can't see more. Because again,
I'm not saying they can't.
Yeah.
I'm just saying the reason why our visual spectrum is where it is because it encompasses like the most beneficiary interval of light that we must see, right? Mm-hmm. Everything else is kind of secondary. Like, if we hadn't invented X-ray machines, what reason would we have to see X-rays, Like, let's say we're cavemen hunting deer. Why do we need to see X-rays, right? Like, it doesn't really make sense. But I guess nowadays when we're studying galaxies and we have like X-ray images of galaxies, which relays different types of information back, I guess X-ray eyes would be kind of cool. But this is why technology is so advantageous, right? Because you can just make X-ray eyes.
X-ray eyes?
Just call it a telescope. Takes pictures. But funnily enough, you see all these pictures, right, of like X-ray images. You also see infrared images, like thermal stuff like that.
Mm-hmm.
One thing that I find like a little bit funny is that these images are actually like the information is translated into visual, like the visual spectrum, but you're not actually seeing like the what it's supposed to look like. Mm-hmm. You know what I mean?
Just we can never. We literally can't.
I know, our brains just can't even process. I guess it could. I guess it's our eyes that just don't function that way. And so when you see like an X-ray image of a galaxy, it's like a dumbed down version, or not dumbed down, or like, you know, like colorblind glasses.
No, I know what you mean, because like there are like on any telescope or any like famous images of any galaxy or something, you can search for all the different spectrums of the image, right? Like you can search for an ultraviolet image, you can search you can search for an infrared image, you can even search for an image highlighting certain chemical elements, for example, right? Mm-hmm. So obviously some telescopes and some software can do that. So there are like, you know, highlights and things that we can do to take it further to see the full image. But again, that's still being translated into visible light at the end of the day.
I have a question for the audience, if anybody knows, actually. Like, when colorblind people put on those special glasses, do they actually see the colors that their eyes aren't able to see? Because I highly doubt that lenses would change like their biological inadequacies, I guess is the word. Like if your eyes can't see red, then how is looking through a lens going to make you see red? The light still has to go through your eyes that can't see the red. So I don't know. Somebody let me know. But yeah.
Yeah, I'm actually reading up this. That was such an interesting question.
I know, because like I see videos all the time of like colorblind people who are like, oh my god, I can see it, but it's like, how?
Yeah,
your eyes are still, the light still has to go through your eyes that can't see the color. But yeah, anyways.
Wow, so I mean, I'm literally looking at these glasses right now that are work for colorblind people, and I mean, apparently, it does not. You know, it's definitely not 100% like a regular non-colorblind person. No way, but it's definitely something. And I'm assuming, okay, colorblind also, that's different though, because, and we can actually get into this because we were talking, or now we can actually maybe talk a little bit about the spectrum itself, you know, going through the spectrum. So technically there are things on both sides, right? We can start with the visible and then we can like, or do you want to start with one side and go to the other? Because I was okay. So like, for example, I mean, the best way and to start with this whole thing, right, is what was I gonna say? The fundamental notion of the electromagnetic spectrum is that light and energy, or the energy that the light carries, is related to this color that we perceive. That is that fundament. So the type of light, the type of placement in the electromagnetic spectrum, when we say infrared, when we say X-ray, when we say microwave, whatever, completely and utterly depends on the energy of that given light. And the energy of that given light depends solely on the frequency of that light, or you can also say on the wavelength of that light, right?
Oh, wait, 1 second. I just got to explain something real quick.
Go for it.
This actually relates to the speed of light. Because hold on. Let's think about something real quick. If the speed at which the wave is moving is constant, right? Then the only thing that can really add energy is the wavelength. You know what I mean? So imagine you have like this interval of, let's say, 1 meter, and you're going up and down, you're waving like slowly, right? And then you have another interval, same length, right? But the wave is moving at the same speed, but it has to go up and down more times in the same interval, right? Intuitively, you can say that the one with the shorter wavelength has more energy, right? Because it has to, like, this is just an intuitive, like, hand wavy explanation. But it's like the wave has to travel more, like, up and down, up, like, very, very, very quickly. Mm-hmm. And it has to make it from one side of the interval to the other side in the same amount of time as the slow moving one, the one that's just going up, down, up. So intuitively, when you shorten the wavelength, there's more and more energy. And mm-hmm. so when you actually study the visual spectrum, you see that the lowest wavelength color, highest wavelength color, lowest energy is red. And then as you move up the wavelength, you go all the way through the rainbow, all the way to purple. And so the reason we call it, violet, sorry.
It's called ultraviolet, man. There's a reason it's violet, you know?
You want me to call it Margaret, I don't know, indigo, I don't know.
Indigo, you have to.
So infra means like under, right? Infrared, under red. Mm-hmm. And then ultraviolet, above violet, okay? Mm-hmm. And then in the ultraviolet range, correct me if I'm wrong, but it goes X-ray, then gamma rays. Yeah. Gamma rays being the highest energy photon type.
So this is going back into that gamma radiation talk, like quick snippet that I was talking about here, with the high energy photons are released. So in radioactive decay, when these electrons are jumping, down onto a resting state, because I mean, when any element is decaying, it releases a bunch of particles, alpha particles, beta particles, gamma particles. And these gamma particles are these photons, these high energy photons, right? And that's on the spectrum. So anything over, and again, these are all very discrete levels. And I believe a lot of it is just, obviously, like, it has been studied and whatnot, but a lot of it is simply our understanding of the spectrum. Like, I'm pretty sure there can very much be higher than gamma, right? Like, what's...
Actually, so this actually ties into the Planck length, because...
But gamma doesn't limit at Planck. There's no way, does it?
Well, the shortest / highest energy
would
photon ever possible would be the Planck length.
Exactly, when the wavelength is equal to the Planck length. Exactly.
And I think gamma ray just like goes all the way.
I guess gamma is just what we call all the way. And we were talking about infrared, and talking about on the other side of infrared, so sub-red, we have radio waves. So these are the most popular type of waves that we use, and all our cell towers, everything, FM radio, for example, is all based off of radio waves, right? Oh, wait, we didn't get into microwaves. Microwaves is after ultraviolet, before X-rays. So that's microwaves. And interestingly enough, microwaves have microwaves. Not a lot of people actually think about that. Like, when you say I have a microwave in my kitchen, like that microwave, the fact that it produces these electromagnetic waves, not a lot of people know that. And these microwaves are, interestingly enough, because they're higher energy than visible light. So we can't, again, see them, right? Because it's higher energy. Anything after the violet, we can't see. So the microwaves basically simply excite the water and heat up the water in your food, hence heating it up. Anyways, I mean, that's another topic. But talking about the microwave in a microwave is an interesting topic on the higher section of light.
Something interesting about microwaves is that the reason why that sometimes, like, one spot is cold and another spot on your plate is warm is because when you turn on your microwave, it creates this interference pattern, this like 3-dimensional interference pattern of like constructive waves and destructive waves inside your microwave. And the way your microwave is actually built, it's made to like annihilate the field outside, like the way the material, the box is actually built. It kind of conceals the whole like deadly warming up part to the inside of the microwave. And then basically, if like one spot on your plate is like not crossing like a constructive area of this microwave field, I guess you can say, then it just, it never gets the effect.
That's also why I guess
the heating up.
The food rotates in a microwave, right? So it can hopefully get all the different parts in case any one particular was not accounted for. So that's actually nice. And also, because you brought up the thing that, it's dangerous outside of the box. So, Jesus, sorry. So all of these higher energy light, ultraviolet included, even ultraviolet, but obviously the higher the energy, the worse, are all carcinogens, almost, you can maybe call them, because they all are cancerous forms of light. Reason being, they are shorter, again, in wavelength. They are shorter and therefore are able to penetrate our skin. And because of that, they are able to mess with the DNA and mess with the tissues, causing small mutations here and there, which then causes along the road cancer, right? So usually that's why you never ever put a pregnant lady through an X-ray, because that could cause cancer to the kid, for example, because obviously lack of whatever. Don't want to get into that part, but I'm just trying to give you the reasoning behind, higher energy. The reason it's also, bad is because it's bad for our bodies, literally because it can penetrate through it. And usually it's what we, relate to cancerous radiation. Gamma radiation is primarily cancer radiation. So when we ever talk about, again, I keep going back to the bombings example. I don't know what's in my head, but anyway, going back to the bombings example, like even if you weren't in the blast radius, there can be a huge radioactive radius. And that is actually even more dangerous, because then your kids will all have some form of mutation. And this has actually been seen in Japanese cities and stuff like that. This conversation got really dark. I'm sorry. But,
right.
But I just wanted to bring up how the relationship between high energy electromagnetic waves and us. Because we were talking about microwaves and dangerous microwaves. So.
Right. Remember when we were talking about your classroom, man? The first day of physics with Rayhan. So you're in a car crash and a bomb goes off.
Oh no! Okay, I misspeak sometimes.
Now you're flying through the windshield and you're getting radiation. You're dying both ways at once. It's terrible.
It's tough. It's a tough life. But anyway, I was talking about radio waves, right, and how useful they are. Because radio waves is on the other side of the spectrum. So anything lower frequency-wise and higher wavelength-wise than infrared, we call radio wave. Now, obviously, we're not telling you the numbers because, it doesn't really matter. The only maybe important numbers maybe we can know is that visible light is from roughly 400 to 700 nanometers. That's the wavelength of visible light. That's the only important numbers. The rest, they're just very particular and scattered around. But that's the big one. But so radio waves, contrary to your higher energy, do not penetrate through your body whatsoever, right? And that is exactly why they are used for communications, right? So when you have your phone and you're calling someone or whatever, right, the reason it's not really that bad for you is because these waves are literally simply passing through your body because the wavelength is so much longer, right? So that's the whole deal. Wavelength longer, frequency smaller, energy smaller, right? So that's the whole deal. It still travels at the speed of light, though. Still travels very much at the speed of light, and that's the biggest thing. All of this spectrum still traveling at this constant speed. All of this that we just spoke about in the last 15, 20 minutes, all of it still travels at the speed of light, but they're just different properties and different things that we can see, and we can observe via all of these methods that we've, come up with today.
And it's pretty funny. I have two things to say here.
Okay.
First thing, when did radio come out, right? Was it in the 20s that radios came out? Anyway, okay, let's pretend it's the 20s. This means that
1906 was the
1906.
first ever radio broadcast.
Okay, so it's been 115 years. So this means that the actual radio, the radio wave sphere around the Earth is 115 light years in radius, right? Meaning that any receptor within 115 light years of the Earth can actually intercept radio transmissions from earlier epochs of our technological advancements. And also, let's say there's an alien chilling at 120 light years away. In 5 years from now, he's going to be receiving the very first radio transmissions that humans ever sent out. Another thing is that, as we talked about, radio waves and visual light waves are, the same breed, right? They're all just different energy levels of electromagnetic radiation, which means that the same concept applies with like visual stuff, which means that if, let's say, an alien civilization with a really big telescope, let's say it's 65 million light years away, they're going to be seeing the Earth 65 million years ago, which means they're going to be seeing dinosaurs. So imagine you're an alien civilization, you're like, all right, let's go and look for life in the universe. You look at the Earth, you're like, oh my God, there's giant reptiles. They would have no idea about what we're doing right now. Obviously, if they have that kind of technology, they would know that, right?
No, they literally can't, though. They literally can't.
No. They would know that they're looking at us in
that's what
past,
you mean. That's what
right?
you mean. Yeah.
They wouldn't be able to assume that what we are now, right?
Exactly.
But that's just something cool, right? Because it's just the photons that were reflected from the sun, reflected off of the dinosaurs in the direction of these aliens, are just now reaching their telescopes, and then they're like, oh, look, there's these giant reptiles here.
Okay, there's a very small chance. I mean, I get your point, but there's a very small chance they can actually see light emitted.
No, listen, this telescope would have to be absolutely ginormous.
Exactly.
But,
it would have to be some next level telescope.
But it's possible. That's all I'm saying. It's possible.
By the way, is your mic audio levels good?
Yeah.
Oh, it's good. Okay, cool. So, and the interesting thing about this whole dinosaur situation, like them seeing this, is fundamentally, when I learned originally in astronomy, and I think this is a big moment for everyone. When you learn, because I don't know, I think this is a big moment for everyone. I think it's safe to say when you learn that the things that you're seeing are hundreds of millions of light years or years ago, hundreds of millions of literal years ago, you sometimes start to think, well, what is actually in the sky right now? And you don't know the answer to that. You know what I mean? You technically never know the answer to that.
And something that's awesome, which we talked about in an astronomy episode, is Hubble's law, right? The further you are away from Earth, the faster you're moving away from Earth. And that's just due to the expansion of the universe, which means that there is a radius around the Earth. There's like the sphere surrounding the Earth, at that point, on the edge of the sphere, you are moving the speed of light away from the Earth. Which means that as soon as you cross that boundary, the photons that are being emitted will never, ever, ever reach the Earth.
And hypothetically, interestingly enough, these galaxies are moving away from us faster than the speed of light.
Yeah.
So everyone's like, what? How is that a possibility, man? And the biggest thing is because now and this is what I love about physics. Whenever we encounter a problem, we either try to find a solution
or we make up a solution.
We just make up a solution. We just okay, dark energy, I guess.
But it turns out it's low-key right.
It turns out it's quite a viable solution. It turns out it does make quite a lot of sense, but I'm just trying to joke on that fact.
Yeah.
But the whole point of this radius that's going to be fleeting from us, it's kind of scary because and I think I've definitely recommended this. I think we both recommended this on a previous episode. I keep mispronouncing the channel. It's not Kurzgesagt. I keep saying Kurzgesagt's video, The Limit of Humanity. Beautiful video where truly he shows in the end how we could come to a stage, and I remember saying this exact sentence, how we can come to a stage where we see nothing in the night sky. And that would literally be, and that will be a future if we stay on Earth forever, obviously. So it's scary.
That'll take a fat minute, though.
Yeah, no, obviously. It'll take a very long amount of time. But the whole point, the point is that that's what's happening. That's where it's going. You know? Like, just because that's not where it is, we can still understand the process. You know what I mean? We're understanding the process that the galaxies are flying away from one another. And one day the universe will be so large that no galaxies will be able to see each other. And it will just be, like, each galaxy will basically be its own island almost, you know.
They would look at ancient photographs of the night sky and be like, this is what the night sky used to look like, and it's like these crazy like images of the Milky Way and everything. That would be so it's like, cool. Whoa. Well, I guess we would still be able to see the Milky Way. But I'm saying like.
Other stuff, like half the stuff would disappear. I mean, I guess not half the stuff, because a lot of the stars I guess if the Milky Way is staying, then a lot of the stars in our night sky would stay. But again, the idea is that a lot of the other, like, still a big chunk of the sky would disappear. A very big chunk of the sky would disappear. But that's just the idea, you know, the fact that these things are receding away, and even light can't keep up with it.
Mm-hmm.
That's tough.
Light itself cannot even, you know, try a little bit harder just to reach our eyes. You know, it goes at the speed of light, but, you know, the fabric of space-time has no limits.
We didn't talk about causality.
Well, I mean, it's kind of the same thing, but whatever.
Because, like, it's always interesting, you know, to talk about, because especially with the whole information argument and how these things are moving at this fastest speed possible. You know, it's almost defining the speed between any two events or any two things happening. Or if we can just have a quick word on causality, I think just the fundamental notion or the idea of causality is a cause and an effect. So every effect has a cause. So the road to causality is always every single event that occurs in the universe was caused by something. And that's just, you know, the idea that physicists and scientists have been following forever, basically. So the idea that there is this fastest speed in the universe, the speed of light, almost points, or does, not almost, it does point to the speed of causality. So the speed between any two successive events, or the speed between causing something and something happening. You know what I mean? So that speed is limited. That's a finite speed. And that interpretation of the universe itself, I think, is quite beautiful. That there isn't, like, you know, any instantaneous effect, nothing like that. Like, it's a quantifiable amount of time or amount of speed between the cause and the effect of any event. And that's also a bigger, or not bigger, but like that's also a neat discovery with the fact that the speed of light is, you know, this fastest, godforsakingly high speed, basically. Yeah, light, really cool, man. Really cool stuff.
Mm-hmm. And I think like a very big barrier in the future is actually going to be the speed of light itself. Because in the future, when technology and, you know, our engineering is going to get better, then what's going to happen is that we're going to have spaceships that can go very, very fast, right? But obviously humans are achievers, right? We want bigger, better, faster. We're going to get to the point where we literally can't go faster without it costing more than the entire Earth is worth, or our entire, like, you know, we're getting diamonds from Pluto and all these resources from different asteroids. But to build that better ship that goes, you know, 10% faster than the previous one is going to cost so much money that we just can't do it. Mm-hmm. And not only that, is that it'll get exponentially more expensive the closer you want to get to the speed of light. Mm-hmm. And then only at that point do you realize how actually slow the speed of light is. Because the speed of light is incredibly slow. Yeah, go ahead.
But the interesting thing about the fact that about the speed of light is the whole universe seemingly revolves around the speed. Yeah. So even though the speed is tremendously slow, the time that passes for you is also relatively slow. So traveling at a very high velocity. So for example, and I mean, I know this doesn't really make sense, but just bear with me. The easiest way to say that a photon doesn't experience any time. That from the time from which it was created at the center of the sun to which it reaches our eyes, it experienced 0 time. And that's simply because of the fact that it travels at the speed of light. Now, obviously, we can't do that. So let's say we go a little slower than the speed of light. The interesting thing about this whole relativity time dilation thing with the speed of light is the closer you go to it, the slower your time goes, right? So you're now, all of a sudden, your 25 light year experience that will take the Earth. So for people on the Earth, it'll take you 25 years. But for you on that actual spaceship, you would be chilling. You would maybe be there in a couple years. You know, maybe a couple. I mean, obviously, the closer you are to the speed of light, it is greatly exponential. So the closer you get to the speed of light, the less and less and less and less it takes. But you can actually do a calculation. And, you know, like a 25 light year journey, if you're traveling at 999 the speed of light, even though that's, I know how impossible that is.
I actually haven't thought about this so much.
It will be a very small amount of time.
But I'm saying if you go close to the speed of light, there's no way that, like, you can do, like, 1 million light years in your lifetime, right?
Not 1 million.
But here's what I'm saying: the observable universe is 90 billion, right? So you can't even do 1 million light years.
No, but we can't use regular space travel for reaching other galaxies.
Yeah,
like we would have to come up with, again, an Einstein-Rosen bridge, a wormhole.
Okay.
You know, we have to come up with something like that because mathematically it exists. We just don't have the technology or the science for it quite yet.
I swear to God, man, it exists.
It does. It does. Right. So we just need a hope.
I believe you.
We just need a hope. Anyways. And I mean, who knows, you know, like science. I mean, I'm not saying in our lifetime, maybe not, but like 1,000, 2,000, 3,000 years from now, which is nothing, by the way, in comparison to the Earth. Like 1 million, 20 million years from now, you think humanity is still going to be on Earth? I mean, if they are, we're done. There's no way. There's no way we're going to still be on Earth. Like, we have to be a multiplanetary species at that point.
Well, yeah, but there's probably still people that are going to be chilling on the Earth. If it's like, here's the thing. I think on the low, like on the low, we're going to save the environment. Like people are going to start clicking when like things really start going bad. Like right now,
I don't know, man. There are a lot of dumb people in this world.
We're not actually like we're not seeing the effects that much, right?
When I'm saying dumb, also, by the way, I don't actually mean stupid. I mean ignorant, and you know, people who won't listen and are necessarily more egotistical.
When things are really gonna go.
I mean, I hope. Everyone hopes, you know. Everyone hopes. Because the thing is, see, here's the thing. Like, there are a lot of problems in the world. A lot of problems, you know. Like, poverty, child malnutrition. Like, there are a lot of problems in the world. Climate change is actually not even, like, top 50. But it's the most predominant. It's the one that everyone's talking about. So everyone's like, okay, climate change. Yay, climate change. But there are a lot more issues in the planet right now, on the Earth right now, that we're not really dealing with, but climate change has just got this big name. So even if we were, but the thing is, we can't like just do any, like right now at least, even in the direction we're going. Okay, EV cars are good. Think twice, man. When the factories required to make the batteries for the EV cars are a lot more a lot worse for the environment than those that make, you know, non-EV cars. So if you actually add up the price of the battery manufacturing to the environment. I'm not saying price money-wise. I'm saying price to the environment, manufacturing the battery versus the price to the environment of, let's say, a petrol car, it's actually not that different. Like, you really start seeing EV not being that much greater. Like, unless we change the way, and I know there are new battery technologies coming out, like Elon Musk with his new Plaid model. There are like new battery technologies, here and there. So it's really cool that we're coming up with those ideas. But unless we get those ideas, climate change ain't going anywhere.
Oh, right.
We need to collectively care about this. All of us.
Yeah.
We need to collectively care.
For sure.
That's what needs to be done.
Let's donate 10% of the proceeds from our merch to go to climate change.
No. Was that the joke? Is there no proceeds?
There's no joke. This is what we're doing. So make sure to buy our merch so we can save the planet together.
Yeah.
Anyways,
one step at a time.
This concludes. It's a wonderful conclusion to our discussion on light.
A pretty interesting one.
Thank you so much for listening to this episode of the podcast. If you have any episode suggestions, make sure to hit us up on Instagram at math.physics.podcast. Make sure to leave a comment underneath this video to become the comment of the week. Follow, subscribe, like. That's about it.
Yep.
Thank you so much, everybody. This has been episode number 67 of the Math and Physics podcast. I'm your host, Parker.
And I'm Ray. We will see you soon.
Bye, everybody.